good afternoon, morning, night, depending on where everyone is. It's really great to welcome everyone to this third webinar from our second international symposium on the application of AI in metallurgy and materials. So my name's Jenny Shepherd. I'm a lecturer at the University of Leicester within the School of Engineering and have been involved with the organisation of this series along with all of our organising committee and our chairs. And so we've previously had two very successful webinars that looked on the applications of AI in material science and engineering, and also a bit more about alloy and process design. But today's session really focuses on the data-driven approach and its application to material science. So if we can just go to the next slide. Yep. Sorry, so if we can go to the slide about, it's a different version of the thing to I've seen. Yeah. So we're really lucky to have three internationally renowned speakers from literally all sides of the world. But before we get on to the scientific talks, we're going to have an introduction from the University of Leicester's President and Vice Chancellor, Professor Nishan Kanagaraja, who unfortunately wasn't able to attend this afternoon, but has given us a pre-recorded welcome to this seminar session. So Shinapat, hopefully we can play this.
Hi. On behalf of everyone at University of Leicester, I'm delighted to welcome you all to this conference in artificial intelligence in metallurgy and materials. Conferences are a key activity for research-intensive universities. It allows us to bring together the greatest minds working in that area, to create new connections, to meet up with old connections, but more importantly, to share the latest development in your field and think about the future of this area. Artificial intelligence is revolutionizing many areas of our disciplines and society as a whole. And I'm sure during this conference you'll come up with new areas to investigate and new partnerships to help us solve some of the problems. I'm aware the last inaugural symposium was very successful in Beijing, and unfortunately we have to have this event virtually. Nevertheless, I want to thank all those involved in organizing this symposium, and I hope you have a fantastic time. Go away with great memories of this virtual conference. All the best. Hi.
Okay, so we now go on to the scientific talks. So how this is going to run is we'll have our three talks and then we'll have questions at the end during a discussion session. So if any questions at all come up during the talks, if you could write them in the chat box with which of the presenters they are focused at, that would be really great, and we can then have a bit of a discussion and answer all of those questions at the end. So it gives me great pleasure to introduce our first speaker today, which is Professor Deshun Xue, who from Xi'an Jiaotong University. So Professor Xue received his BSc and PhD from Xi'an Jiaotong University, spending time during his PhD at the National Institute of Material Science, Tsukuba, Japan. He was then a postdoc at Los Alamos National Lab in the USA before he returned to Xi'an Jiaotong University in 2016. He's currently a professor of material science at the university and has published prolifically with a particular research interest in materials informatics. And he's currently accelerating the search for new materials using machine learning and optimization algorithms. And his talk today is entitled Active Learning in Searching for New Materials, with emphasis on efficient sampling using uncertainties. So it gives me great pleasure to pass the floor over to Professor Xue.
Okay, thank you. Thank you, Jenny. So I'm going to share my screen. Okay.
Yep.
So I'm De Xue from Xi'an Jiaotong University. It's my great honor to have this opportunity to share our recent progress on the material informatics. My title today is Active Learning in Searching for New Materials with emphasis on efficient sampling. So first, I would like to thank my collaborators, Dr. Ding, Professor Sun, and Professor Zhou in Xi'an Jiaotong University, and also Tarab and Prasanna from US. And most of the work is actually did by my students. I have 3 postgraduate students, Rui Hao, Tian, and Yun Fan. And I also would like to thank those fundings for the financial support. So there is a big challenge in developing new material is that the search space of the new material is very high dimensional and very complex. That's because there's many tuning knobs to control the property of the material, such as the chemical compositions, the processing conditions, and also like the microstructures, phases, and crystal structures. So those complexity makes the discovery space very high dimensional. So there are millions or hundreds of millions possibilities for us to explore. But what we know is only a very small fraction of experimental data. So the big challenge is how to, from this small fraction of the data, to efficiently explore the huge search space, discovery space. That's what we think the big challenge in the material science. So let's define the searching for new material in this way. So we think the development of a new material is an optimization problem in this very huge search space, which is consisted of compositions, processing conditions, and etc. So we want to find a material. We want to find a material that have the targeted properties maximum. So if the space is very simple, only have one unique optima or minimum, so it's very easy for us to find this minimum. So we do a series of experiments and we can easily find such kind of minimum. But actually what we meet is we have a lot of sub-minimum, and we cannot directly get the global minimum. So we need to do many experiments to explore the whole space and find the one with the best targeted property. So we then can employ the machine learning or the statistical inference to make predictions for those possibilities in such a large search space. So based on the existing data. So the machine learning help us to build the mapping or the functional form between the features, the X, such as all the material descriptors, such as the compositions or processing conditions, to the Y is the targeted property. So if we have such kind of functional form or the mapping, so we can directly go to the global minimum. And those predictions allow us have a quick identification of the targeted material with the optimized compositions and processing conditions. So the traditional data-driven approach usually consists of accumulating large amount of data and then build machine learning models on such kind of large data, and the statistical inference learn from the data and get the mapping, get the functional form, then use this kind of functional form y equals to fx to predict the unexplored space, and then predict the properties of the search space. Based on the predictions. So one can select the one with the best prediction to do simulation or either do experimental synthesis or characterization. Once we get the experimental results or simulation results, then we feed the data back to the database. So then we can do the learning again. We're using such kind of iteration loop to drive the search for the new material. That's the traditional data-driven approach. But usually we met a small data problem in material science. So unlike the data size in Google or in Marie, which have the petabyte or terabyte, those large data. So in material science, the data is quite small. It's usually less than 1 gigabyte, or especially for the experimentalist. I'm myself is an experimentalist. So for a particular alloy system, we usually have like tens of samples or 100 of data points. So that's all we have. So this is not especially in the experiment part, this is not a big data problem. I think it's a small data problem. So due to such kind of small data problem, so the number of the samples or the number of the data is very limited. So based on such kind of small data, we make the statistical inference. The model is not necessarily optimal. The prediction may not be good. So if we use such kind of predictions with large uncertainties to guide the experiment, so we don't think the guidance will be good. So then such kind of a loop may not efficient. So to this end, in order to overcome such kind of small data problem, we proposed such kind of adaptive design loop to accelerate the search for new problem. So the green arrows shows the loop of the traditional data-driven approach, or the big data-driven approach. So the blue one is what we did. So we want to start from the database. Usually it's a small database. Then we build a statistical inference or machine learning models. These models are predictive, but the predictions can contain a large uncertainties. So based on the model predictions and uncertainties, we add a panel of adaptive experimental design. We use this panel to choose the most informative sample to get the most valuable experiment, and then use this experiment design part panel to guide the next calculation or next experimental characterization, and then feed these back to the database and do the loop again. So the key here is we introduce the optimal experimental design component, which will efficiently sample the most informative experiment. So that is the approach we are going to use. So in order to demonstrate such kind of a loop is very efficient in searching for new material, we first want to show a simulated case, very simple two-dimensional case to show our idea. So here, suppose we want to maximize the y-axis by varying the x. We can consider x as like the aluminum contents in the titanium alloy. So the question is how to find the best x to maximize the y. So if we know the actual distribution of y with x, it's quite easy, right? If we know y equals to fx, Then we know the red dot curves. It's quite easy. We believe the red curve and we find the X optimized, which correspond to the Y max. So that's the best material we are going to find. But the reality is we don't know the functional form. We don't know the red curve. So how to find the best X to maximize Y? So we can employ the machine learning algorithms. So there are many algorithms can be employed to estimate the curve. So here we refer to such kind of model as a regressor. Actually, it's a regression model. So the simplest one regression model is the linear model. So we fit the 3 data with a linear model. And the green line is the linear model, and the points in the green line is the prediction of the Y. So we can, which one is going to do for the next experiment, we choose the one with the highest prediction. So we refer to this argmax Y as the selector. So we select the material with the highest predicted value. So then we do the experiment, but the result is not good, right? As the red dot shows. But the good thing is we have 4 data points. And we update our linear model. We update the parameters in our linear model, and then we have new predictions. Then we use the selector to select the next experiment point. The star shows the next experiment. We do the experiment. The results are not good, but we have 5 data points. So what we did is we started from the data and we do the regressor, we do the statistical inference. And then based on the best prediction, we do the new experiment and we feedback. Then we do this loop again and again, and until we find the highest Y. So actually, such kind of a loop is a big data loop. It's not very efficient if we have very small amount of data to start with. So we almost tried all the possibilities to find the maximum value. So we do the like more than 90% experiment to find the best material. So one way to improve the efficiency is to find a better regressor. For example, here we try the polynomial model, we make it a little bit nonlinear. So again, we do the experiment again to do the loop again. So we almost try all the possibilities. And we tried even more experiments than the linear model. And this is not very good, so we can put our domain knowledge. We have the physical models or the empirical models, which help us to find a better estimation of the real function. So we give a very nonlinear model with multiple maxima. So it's very close to the real distribution. And at this time, we do the loop again, and we only try half of the possibilities. So as we said that in reality, we have millions of possibilities. So if we try half, this is far beyond our capabilities to do experiment or even calculations. So then we put our experiment design panel into this loop. So we from data to do the regression, we build the statistical inference. With this inference, we can have the predictions. The most important thing is here, we must incorporate the uncertainties. So using this design panel, we select the next experiment. It's not necessary to be the best prediction. It can be another point, but more helpful to build a better model. So again, we start from the linear regression model, but we use another selector, what we call it the efficient global optimization. So we have the regressor as the linear regression model and the selector is the equal efficient global optimization. So you will see here, so we are not going to choose the best predicted value. We choose another point which is more helpful to the model. So we tried a quarter of the possibilities. It's faster. So we can also combine the polynomial model with the selector. We now do the 16 new experiment to find the best value. And if we combine all the panels together, we put our domain knowledge to make the statistical inference better and better. And then we put the adaptive design panel, adaptive design panel to help us to make decision. Then we can have a very good results. So the optimization process was accelerated. We only need six new experiment. We just need 6 new, sorry. Okay, I want to just show this video again. So we just need 6 new experiment to find the maximum. So we say that the informatics may accelerate the discovery of new materials. Okay, in the following, I'm going to show 2 case studies which we use the sort kind of adaptive design loop to actually find some new material or the material with better properties. So the case study 1, what I call is the selecting the selectors. I want to show which selector so far is the best for the material science, especially the experiments in material science. So we have the data, usually it's very small, and we build the statistical inference. We can have many different models. We can have linear models, we can have kernel-based models, we can have tree-based models, and we can also have like the neural network or deep learning. Then this kind of statistical inference is predictive. It can be applied to the unexplored candidates and give the predictions of those candidates. So here, the unexplored possible candidates is the number is very large. So with this predictive model plus this unexplored space, we could have thousands of or tens of thousands candidates with predicted property. So next question is, which candidate should we do experimentally? You know, in experiment, we cannot do so many at a time. So consider the cost. So we may only make 1 or 2 alloys. So the question is how to select the candidates for the next experiment. So that's the select data. So what the select data is help us to make decision which experiment to do. There's many different kinds of selectors. Usually it can be divided into such kind of 4 categories. The first one is try and error, which is we do it randomly, and the second one is exploitation, and the third one is exploration, and the last one is the balance trade-off between the 2. Okay, let me explain it one by one. So exploitation is what we believe we are going to believe the machine learning model or the statistical model. So look at the picture. So the blue points are the experimental data, are the real data. And we build a machine learning model to give the prediction for the rest points. So the red line is the machine learning model. So exploitation means that we believe in the model. We think the model is 100% correct. So if we think the model is correct, then we believe it, we will choose the one with the highest predicted value to do the experiment. That's the exploration. Exploitation. And that's the one extreme end. So we go into the other extreme end. So we have 5 blue points, which are the real data, and the red curve is a machine learning model, and then the gray curves are all possible machine learning models, or we can consider that's the uncertainty of the machine learning model. So where the gray curve span a lot means the machine learning model have a large uncertainty. So here we want to add more points and points to improve the machine learning model. So we want to choose the one with largest uncertainty to help us to improve the model. That's exploration. But in reality, we don't know our model is perfect or our model is totally bad. So we need some balance trade-off between the exploitation and exploration. So here, this figure just shows some selectors. So see there are 1, 2, 3, 4 new samples. The height of the bar is a predicted property. So if we follow the best prediction exploitation, we will choose number 4 sample. But the prediction may not be so good. It contains some uncertainties. So the normal distribution above it is the uncertainties. So the blue horizontal line is so far the best performance. So if we integrate the shaded area, that is the possibilities to improve the property, to get a better property if we do the experiment. For example, if we integrate the shaded area for sample 3, so that is a possibility to improve the material, improve the property if we did number 3 sample. So this is the possibility. If we times the possibility with the improvement and then we calculate the expectation, then we can have the expected improvement. This expected improvement is related to the uncertainty and also related to the predicted value. So using this expected improvement, we can balance trade-off the exploitation and exploration. So by the balance trade-off exploitation and exploration, so the next experiment is not the one with highest predicted value, and it's not the one with highest uncertainty. It chooses the one as the dotted vertical vertical line shows. So this is the different selectors. So we use a model system of baryon titanate-based ferroelectrics to benchmark our approach. So the targeted property here is the electron string. So this kind of material can have string if we apply the electric field. So we want the string as high as possible so that we can make the device smaller. So the data and the search space is, we have 61 known data. So these 61 data, we have real properties. We build the model on these 61 data points and to search for the new material in these 500,000 possibilities. So we use the Sarkam design loop, and we use different selectors to choose different experiment, and we see which selector choose the best material. And we build the machine learning model, and we do the feature selection, we do the model selection, and we find the SVR-RBF is the best model, and it can give us the prediction. And here is the results. So please see the left-hand panel. So we plot the measured string as a function of iteration loops. So 1 means the first iteration, 2 means the second iteration. And the points in different color means we select them from different selectors. It can be seen that the balance trade-off selector will give rise the best results. So within only 3 iterations, we do 3 more experiments, we can improve the electron stream by 53% compared to the largest one in the string. So this is very efficient. So using such kind of selector to help the machine learning model, we can very quickly to find the best material. And we explain our results by the DFT and both phase field simulations. So we would like to say that the balance trade-off between exploration using uncertainty and the exploitation using the model predictions is a good optimal criterion for guiding the experiments in material design. So here's a case study 2, which is actually the alloys, the night chip memory alloys. So this is the chip memory alloys. What we care about is the thermal hysteresis. You know, there is a phase transition in such kind of material. So we want the heating transition and the cooling transition occurs at one temperature. So the search space is very large and the known data is very small. We have 22 known data, but we almost have 0.8 million possibilities. So we use such kind of design loop to find the best material. So here, this figure shows our practice is using our training data to find the best regressor and selected combinations. You know, there are so many combinations. We use our training data to pre-select the best one, regressor and selected combination. And again, only use 6 iterations. We find the lowest chip memory alloys, thermal hysteresis, I mean. So this is our new, our new design new alloys, and compared to the commercial 950, it's the thermal hysteresis is greatly reduced, and we have a better thermal stability, and the temperature, the shift of the transition temperature is very small. It's 0.02 Kelvin. And so let's go to the final conclusion. So our work provides a framework for accelerate the discovery of new material, especially from experiments with small data sets. And we use uncertainties in the measurements or the model predictions to guide the next experiment. And we can have the budget or cost considerations. And our cost focus here is iteratively refine the predictions to minimize the number of new experiments or calculations we need. So that's the consideration of design and uncertainty efficient sampling. So that's all for my talk. Thank you very much. I hope I do not spend too much time.
No, thank you very much. That was excellent. Shinapak, could you quickly go back to the outline slide, the schedule? Thank you. So thank you very much for that really informative talk, Professor Xue. So next, I'm really pleased to invite Dr. Enzo Liotti from the University of Oxford to give his talk. So Dr. Liotti's background is in materials engineering with undergraduate degrees from the Politecnico di Milano and a PhD from the University of Loughborough. He joined Patrick Grant's group at the University of Oxford in 2011, and he has a real focus on in situ imaging of solidification with particular research interests in X-ray synchrotron techniques. And so his talk today, it's on the study of nucleation in aluminium alloys using X-ray radiography and machine learning. So I'm delighted to hand over to Dr. Liotti.
Yeah, thank you very much. I'm gonna share my screen. Okay, can you see the presentation?
Yeah, perfect,
yeah.
Thank you.
So thank you very much for the very thorough introduction. And first of all, I would like to acknowledge, to thank the organizer for this webinar for the invitation. In this presentation, I'm going to talk a bit about, as says the title, about a bit of the work we have been doing at Oxford in studying nucleation of aluminum alloy using in situ X-ray imaging. And in particular, of the use of machine learning that for us has been fundamental for extract essentially quantitative information out of the data we have been collecting along the years that would have been otherwise unobtainable. So the work I'm presenting has been done through using a grant from EAPSRC, which is one of the council that fund research in the UK, and it's called Future Liquid Metal Engineering Hub. And is a big multi-collaborative project which involves 5 universities in the UK, Brunel University, which is the leading on this project, and then the University of Leeds, Oxford, Manchester, and Imperial College. The work I'm presenting today has been done with my colleagues in Oxford, so Professor Patrick Grant, who is the leader of the group, Andrew Lui and Robin Vincent, and then Carlos Arteta and Andrew Zisserman at the Department of Oxford Engineering, who developed the machine learning algorithm, and Alexander Rack, which is a beamline scientist at ID19 beamline at the SRF. So a little bit of introduction about why we study solidification. Well, if solidification science underpin many of the critical sector in the metal industry, and in particular, if we look at the metal processing chain, solidification is the first step. In fact, pretty much any metal component has gone through like the liquid to solid transformation at some point, either by casting or gas atomization. Therefore, the microstructure that are developed during the solidification steps have a very strong influence on the final product properties. And what we are aiming to, and why that's the reason why we study solidification, is to basically learn how to manipulate this microstructure to be as good as possible in the first step. In particular, if we look at casting and aluminum alloy, if you do try to cast something, probably what you obtain is exactly what you see in the image, something that is a columnar coarse microstructure, right? That's the typical, and let's say call it natural microstructure you obtain when you cast something. But what you would like to obtain is a grain refined microstructure. So that means like where equiax fine anisotropic grain form instead of this columnar dendrite. The two, I mean, these retain many advantages towards the compared to the columnar one. Is, you know, mechanical property are better, you get lesser defect and so on, less macro segregation. For aluminium, the most used methods to obtain an equiax microstructure is to inoculate. Inoculating means that you add micron-sized particle, extrinsic micron-sized particles, so they don't dissolve in the liquid metal, that act as a nuclei and form and enhance basically heterogeneous nucleation. This technique is widely used in the aluminum industry, and there is one particular particle which is called titanium diboride, which is ubiquitous use for aluminum. However, the process is very inefficient. I mean, only 1% of the seeds are added nucleates, and this is actually has been already optimized along decades. And also the technique or the inoculation, it works for the primary grains, but it doesn't work for the secondary phase, like the intermetallic phase. So any improvement in the efficiency, even increasing the efficiency from 1 to 2%, or to find a grain refiner for intermetallic phase, would actually have a very strong effect on improving the material and component properties. Traditionally, metallurgy or metallurgical studies in general, but study of nucleation in particular, have been done post-mortem. So there is quite a long history for the research in this field, but it's all done by microscopy or chemical analysis of post-mortem samples. So you prepare 10 samples with different conditions, and then you cut them up and you look with a microscope. However, in the last since the early 2000s, late 90s, with the advent of what is called third generation synchrotron, for example, ESRF or APS or Spring 8 in Japan, in situ imaging technique such as like X-ray radiography and X-ray thermography, reach enough spatiotemporal resolution to be able to catch the dynamic of solidification. And for a phenomenon like solidification, this is very important because looking at the dynamic of the grain formation and growth and nucleation allow you to basically start to study the underlying physics phenomena that take place, and therefore learn how to manipulate nucleation to obtain like microstructural tuning or like control of microstructure. A typical imaging experiment in radiography, so an X-ray radiography is essentially, it's not much different than when you go to the hospital and you get a radiograph. So in the setup designed for solidification, we normally use what is called a Bridgman furnace, or essentially there is a furnace with two small plate heater, like you can see here, that are aligned vertically and have a gap in the middle. And the sample is positioned touching the two surfaces, and it can actually move up and down in certain condition. And then the X-ray pass through the middle in the gap, and the transmitted X-ray passing through the sample are collected by an optical system that transforms the X-ray into visible light and then collected by a camera. In this setting, which is very simple, and that's why it's very useful, samples tend to be foil samples, so the thickness vary, but is normally around 200 micron, and this is actually to maintain basically a single layer of grains or crystal forming and not overlapping. So if you do it well, then you can collect images or videos and obtain some kind of data. Yeah. So this is another detail of how the furnace look like when it's set it up. This is the one we use for the data I'm going to present. And the setup is actually an ESRF in one of the beamline. You can see or recognize the two heater, one here and one here in the sample. And in this case, the arrangement was horizontal because we wanted to control the thermal gradient as accurate as possible and avoid what is called like thermosolutal convection. Okay, so I'm going to show a first set of data. You can see here there are 3 videos ready to start, and they are an aluminium 20% copper sample, which was added with this magic powder, the grain refiner. Right in the heater, were essentially on the left and on the right, as you see before the sample was positioned horizontal, and what we call near isothermal conditions. So near because it's essentially there is always a little bit of thermal gradient. And what the difference between the 3 videos is the cooling rate. So if I start the video, you will start to see the grain forming, like these are actually small aluminum dendrites forming from the liquid. This is initially liquid. And of course, because we are cooling at 3 different cooling rates, the time or the evolution of the solid fraction is different. However, even by eye, you can qualitatively see that the grain size on the right is much smaller than the one on the left. And that's because, 2 reasons, because of growth and because of the nucleation is more copious, right? This actually is the effect or a known effect of what happened when you cool faster. Normally you obtain a much finer microstructure because you nucleate or you enhance nucleation. In a similar comparison, these show the effect instead of like the solute content, so different alloys. So when you actually increase the content of the solute element, in this case from a 10% copper to a 25% copper, and these were cooled, these 4 samples were cooled at the same cooling rate, which was 0.7 Kelvin a second. And again, there is a lot of variability, as you can see. I mean, the color depends on it, but this was kind of almost raw data, so that's why the color is different. But you can see the morphology, these are quite large and form quite quickly, despite the cooling rate is the same in all of them. These tend to be kind of smaller, more equiax. And generally, there are a lot of detail that can be picked by eye, and they are very important to understand the underlying mechanism of nucleation. However, the difficulty is how to extract this information. So to give you an idea, in the years we've done on this specific experiment, more or less 55 days of beam time, during which we have collected more than 1,400 video sequences, which account for about 50 terabytes or more than 10 million images. cover a wide range of solidification condition, change different alloy, and even use a little electromagnetic steerer to move the liquid and steer. However, these are very beautiful data. The point is, what do you do with them, right? So you got a lot of information contained in this data set, but the problem is extracting them. So for example, things that could be interesting from a point of view of nucleation is start to count the grain and estimate the formation rate. And also interesting information could be quantify the grain grow rate, either individual grains or the overall kind of grow, and measure solids filled in the liquid. From this specific setup, information can be obtained of the composition of the liquid nearby the grains, and also fluid and grain flow could be done if the grain could be tracked. And then with all this information, nucleation and growth theories could be tested and verified. And bear in mind that solidification science is a field in which there are many and long-standing theories. The problem is there is no experimental data to validate them or disprove them. So even for the task of counting, it's something that could be done by hand, but that would means, if we're speaking about even 100 videos, that somebody would have to go every single frame and then start to put dots to count the grains, and then go in the next frame and do the same. So that would be, you know, a few, maybe hundreds or 1,000 frames per experiment per 100 times. That maybe can, you know, it's time consuming, that could be done. However, when we start to look at quantification of grain growth, so if we want to actually learn about the growth of each individual grains, or measure basically what is called nucleation under cooling, and that require measurement of the solid feed, that became unfeasible manually by a human, right? Therefore, in collaboration with the Professor Andrew Zisserman group at Oxford Robotics, we developed a machine learning algorithm, and the peculiarity was that it required a minimum amount of training. So out of the 1,000 videos, we used only 6 of them, to which I had to manually count and put the dots on the left. The algorithm was then learning from that and detecting the grain in new videos. And we used that essentially with 6 training set. We analyzed so far 128 experiments. And the algorithm was outputting a map allocation of the grain, to which then we added a second part of the algorithm that was tracking the grain and doing the, let's say, solidification parameter measurement. So giving output of the formation rate, grain size, grain growth, what we call nucleation under cooling, and then other things like the diffusion length, which are measurement of diffusivity and grain movement. And this is an example. So that's the algorithm tracking the grain, detect them when they form, and then the bounding box is actually giving you an idea of the size, although the contour and also the primary and secondary arm is generally tracked. The arrows give you an idea of the velocity. So this is quite rich information that can be extracted, that honestly, that this cannot be done by hand. Maybe the counting, yes, but tracking 4,000 of grain, the grow is unrealistic. One use of this data is summarized in this table, which account for 14,000 nucleation events. So this is the kind of number, right? So bear in mind that in solidification, as the presentation before, experiments are quite difficult. So collecting data is not so straightforward. So being able to record hundreds or thousands of video and then manage to extract 14,000 points is a great thing. Also because then you can start to look at correlation between various parameters and actually look at the phenomena in from a statistical point of view. For example, these graphs show that the formation rate, so the rate at which crystal form, increase with the cooling rate, and that's actually expected and known. But also there is a correlation between the cooling rate and the solid content. So strictly speaking, the formation rate increase with the cooling rate and the solid content, but the two are correlated. For example, increasing the solid content has an effect only when you increase the cooling rate. A low cooling rate, essentially, it doesn't have an effect. This is a new finding that was found thanks to actually the very large amount of data that can be generated. A second very important measurement that we were able to do is what is called measure for each individual grain, the nucleation under cooling. The nucleation under cooling essentially is is effectively the driving force that is necessary for a grain to form. So these nuclei sit already in the liquid above the melting point. When the temperature of the liquid is decreased below the melting point, there is still some energy barrier that need to be overtaken for these nuclei to form a grain. And this is very important to understand how nucleation works and how it can be improved. So the algorithm was finding, for example, if we take this little square here, was actually detecting these 5 grains and then going backwards in time and essentially trying to search the first frame in which in that specific location where the grain formed, the grain was not yet formed. And then by measuring the solute concentration at that specific point, this value called undercooling could be measured. And by doing this, the algorithm was able to detect and measure 6,200 nucleation event. And again, this is the first time that in metallurgy we can measure nucleation under cooling directly for each individual grains and not as an overall value. Again, very interesting results correlated like before as a function of the cooling rate and the solute content. And the behavior is in a certain way is expected. Undercooling are very small, as it's known from theory. And so that's a confirmation of many of the theory. But interestingly, for example, these actually undercooling curves essentially decrease with increase in the cooling rate. This is actually not what is believed in the normal in normal believing, in the sense that normally it's believed that the effect of cooling rate is that it increases the amount of undercooling and therefore you get more nucleation. What we actually show with this data is the opposite. You increase the undercooling and nucleation happen at lower, sorry, you increase the cooling rate and nucleation happen at lower undercooling. And it will be clear later why. Finally, another insight we found is that by analyzing the crystal formation rate, we found or confirmed that nucleation happens in bursts and is not a continuous phenomena. This again has been predicted in theory, but these data are the first experimental evidence. As you see here in the graph, is plotting the real-time crystal formation. There was a first wave, and then there will be a second wave in a minute, in which the crystal form all in burst essentially, right? So, and they don't actually form continually. So now there is a moment in which there is low nucleation, and then there is a third burst. Again, applying this methodology to all the 128 data, we found that these waves or bursts are correlated to the solute content, both in intensity and in frequency. Therefore, increasing the solute, what essentially has the effect is to increase the intensity and the frequency of these bursts, and therefore increasing the number of grain forming. So essentially decreasing the grain size. And also we developed our own model, or our own like empirical model to basically describe the effect of cooling rate and the effect of solute, like in terms of nucleation. So I arrived to my conclusion, like in my field in solidification, X-ray imaging allow you to basically catch the dynamic of the phenomena and actually start to look at the underlying physics. And it has become an indispensable tool for the study of solidification. It needs, I'm a strong believer that automated data analysis, in particular machine learning, are a tool that is necessary nowadays to exploit this large data set and extract all the information, and also to find new insight for the strength that actually machine learning can look at data in several and find correlation and actually analyze thousands of data. And I think, and going on, at least in the field of X-ray imaging, machine learning and AI will become an indispensable tool as we are going faster and larger. So with this, I conclude my talk.
Thank you very much for that fascinating talk and showing just how beautiful solidification can be. So it gives me great pleasure.
Yes.
To
Jenny, I just want to say something that, I mean, if
yes.
you have any question, please leave it in the chat box, and then we will pick up in the panel discussion after this the keynote talk. So please feel free to fill the, I mean, to type your question and probably indicate the speaker who you want to address your question as well. That would be great. Thank you.
Yeah, sorry. Thank you very much for that, Shinapat. So yeah, it gives me great pleasure to announce our final speaker, which is Dr. Victor Castillo from the Computational Engineering Division at Lawrence Livermore National Lab in California. Victor's got over 30 years experience in industry and government research within computational physics, machine learning, and basically anything to do with computers. And I think the thing I liked most from his bio was the fact that he was also honoured with the 2013 Community Service Award from Great Minds in STEM. And so, yeah, it gives me great pleasure to welcome Dr. Victor Castillo with his talk on faster prediction with AI. Thank you.
Great, thank you so much. I'd like to thank the organizers and hello from California, from sunny, smoky California. So I'll share my screen, and there we go. So today I'm going to speak about using machine learning along with simulations. So what I'm doing in the bottom line is doing a lot of very high performance computer simulations and using that as data for machine learning algorithms. This is very advantageous to industry, and I'll talk about some of the projects that we're doing. So the U.S. Department of Energy provides a lot of funding for our national labs to help the U.S. industries. And the main reason is that these industries use about 25% of the U.S. Domestic energy, the national energy. And so it's such a big cost to the manufacturers, and additionally it generating a lot of greenhouse gases. So we put a lot of effort into helping them optimize their systems through simulation and machine learning. So what industry needs, the manufacturing industry needs that we find is rapid prediction. They want to be able to do their prediction very fast, and they use simulation often for this, but we are able to improve on that. They need to integrate their production data with their simulation output. If they do have simulation output, often they do have a lot of data from from instrumenting their processing. We can actually combine those together in a good way, in a informed way. And also we need to inform their decision making. Often they have decisions about whether they should put in more sensors, run more simulations, or do more experiments. So we can actually help them quite a bit in that making those capital decisions. And so I'm going to give a couple examples. The first example is from the glass manufacturing industry. This is so if you notice on the right, there's a picture of me and a couple of summer students. We're in front of a glass furnace. Now, this glass furnace is about the size of a small house, what we call a ranch style house. And there's a little port there. You can actually go up and look into there and actually see the molten glass, where the glass is being melted, or the raw materials are being melted and forming the molten glass. You can actually approach the window and look through a welder's glass to actually see it. This is a cartoon that shows. This is a cartoon that shows how this the glass is processed in this tank. So up in the upper left-hand corner, you have the raw materials coming in, and they move in through the they sink in, and the idea is they need to stir this up, and you cannot put an impeller in there because it's molten glass. It's just too hot. So they need to figure out a way to mix the material. So they can the industry has come up with a clever way of putting these burners up at the top, and the heat moves through the glass and is reflected off of this off the bottom, off this reflective material at the bottom, this refractory brick. What this causes is an outgassing of the raw material. The outgassing causes a buoyancy, and this buoyancy causes a convective these convective loops. These convective loops are actually producing the mechanical agitation and stirring necessary for the product to mix properly. So it's all about adjusting the heat distribution at the top, along with a few other mechanical assistance, like gates and other ways of mitigating the flow. This causes the proper mixing in the glass tank. One thing that you get is some of the problems is with the outgassing, you can actually get the bubbles coming to the top and the foam rising to the top and moving towards the forming. And so what they're trying to do is get the foam moving to the left so that it subducts and it subducts and is dissolved into the molten glass. Another problem is if the convection is too vigorous, it will actually cause the raw materials to go out toward the forming, and then you have uncooked raw material. And so they're constantly having to adjust the gas burners to mitigate these defects, these production flaws. And so what I'm showing here is a simulation that the simulation that we're actually, or the GUI that we have derived, and this is the finished product for us, what we've provided to the user. And we've taken a lot of simulations, and we've trained a machine learning neural net, and then I will demonstrate that here. So right now I'm showing the actual GUI, and this is it's obfuscated. It doesn't actually have the real data to protect their IP. But if you notice that I can make adjustments in real time, I can make these adjustments like what happens if I change these gas port distributions. And you'll see in about 10 seconds, we get the new velocity distributions and temperature distributions within that tank. These are based on the simulation predictions. And then additionally, after they run the simulations, the CFD, they run thousands of tracers through there, and these tracers mimic the flow of the path of the raw materials. From that, they can actually get these post-processed calculations that based on the distribution of what these particles are seeing, what kind of heat flows they're seeing, are they being overcooked or undercooked? And then they produce these post-processing indices that are the simulation predictions of the quality, the quality indices. And we can actually match that up with production plant flaw data, and I'll show that in a second. And so if I go back to another example is from the aluminum industry. So I thank Professor Lieta for showing about aluminum. This is actually a casting of a much larger bar ingot. These ingots are in production are about 5 foot across, about 60 inches. What you see on the lower right-hand corner are these pilot plant scale ingots that are done for experimentation. And then you see myself and my collaborator from Oak Ridge National Lab visiting the plant. And we ran simulations, and I'll show the output of the simulation. This movie shows the actual simulations that we ran in a commercial software called Procast. And what we're showing is over time, the ingot is forming. There's a solidification, and when it solidifies, there's actually some residual stress baked into the ingot. And if that maybe I should go back to show you in the beginning here. Yeah, with the residual stress, once the ingot solidifies, you can get these cracks forming. And this is actually a very big problem for the industry, in that end would have to be cut off, that material would have to be reworked, and then they would have this inconsistent sized ingot for rolling, because they can't send this ingot as is into the rolling process with that crack. Additionally, there could be cracks on the surface, and that would actually have to be manually machined off. So this could be very labor intensive. So this preventing these cracks, preventing the residual stress is actually part of the project. So what we can do is simulate where the residual stress is, and predict it. These simulations here take about 24 hours actually to run, 24 to 36 hours. What we're doing is we're learning the simulations, and the output of the fast running surrogate model, like the one for the glass, can actually predict the output in seconds. And so what I'm showing here on the left is a case where there's no cracking, there's no residual stress, and we actually have a distribution of the hot tearing indicator, which is a measure of residual stress. And the distribution shows a very low average for the hot tearing indicator. In the right-hand side, we have a case where there's a lot of residual stressing and likely to have cracking, and you can see the distribution is much higher for the residual stress. So our approach is what we refer to as scientific machine learning. We are using the physical simulations for the training. We're training a deep neural net, and then we have this machine learning algorithm for fast inference mode. And the reason, the main advantage here is that the simulations can be very expensive. And so for the company to run these simulations over and over again can be very costly and time consuming, whereas the inference model can be run pretty much on site in the production facility on something like a gaming laptop. And when I say gaming laptop, that's something with a good GPU, a graphics processing unit in there. Now we can improve the simulation cost by doing intelligent sampling and speculative sampling, and this is very similar to the active learning that was discussed earlier. And again, another concept that we've hit upon today is design of experiments, and the idea here is that we want to set up a design of experiments that can cover the design space efficiently. So the design space might be a high dimension, 10-dimensional, for instance, or depending on how many knobs, say, the system, the plant has to control its process. And when we do certain designs, like this box Benkin design, we can rotate it to cover existing data. So there might often these companies have a curated data set, and so we can figure out how we can leverage those, and then run the additional runs to cover the design space efficiently. And we also want to make sure that we're avoiding certain corner points that are not physical. So a lot of times the corner points, like where all the control parameters are at the max or the min, are actually not a viable solution. So we want to carefully avoid those with the design of experiments. And again, here's an active learning example. We have this system called Merlin that we run on our high performance computing. What it does is it allows for these agents to run, and you can see this diagram shows these agents running these different simulations. And agent 1 might be in this region of design space that I'm colored gold. And agent 2 might be in this part of the design space where I've colored blue. And they run on, they have a idea of a model. They have a prior model that they're running on. And this is seeded from doing an initial design of experiments and coming up with a basic model. And so if agent 1, for instance, is in this area and the simulation is agreeing with what the model is, then it's green. And then it might go over, might stop in the middle of that simulation and actually continue in a different area in this blue region. And that saves computational resources so we can do more simulations. And so this is this active learning algorithm that we're called speculative sampling. So now it's coming over to this area that's in this blue region, where maybe the agent here has compared its simulation with model A, and it's not doing so well. That's where the red dot is. At some point, they come and they publish their data. They're constantly publishing their data, but a new model is published, a model B, and then they can go on and continue. Now there is this idea of explore versus exploit that we leverage, and in some cases the model might actually agree with the simulation. And so instead of having this agent move off to a different area, it might complete the simulation in order to compare it, to gather more information. Is our speculative sampling algorithm doing well or not? And so we can continue on in this fashion. With transfer learning, we are actually taking data from the plants and elevating the physics-based model that's already been learned to actually mimic the plant data better. Now, sometimes these plants are well instrumented and they're generating tons and tons of data, but they're not efficiently exploring the design space. So the data is actually lacking in some respects. We can run the simulations all over the design space because it's a lot cheaper. We don't have to worry about damaging equipment. And so it's better to generate the physics with the simulation and then adjust it with this transfer learning mechanism to mimic the experimental or plant data. And to do this, you take the deep neural net and you freeze all but some of the last layers, and then you retrain on the experimental data. And since the experimental data is sparse, you actually have fewer weights to train. So this is a better way of doing that. And then you can have a retrained, elevated model that incorporates the physics and the true production data, the true ground truth. And so this approach, again, we're calling it scientific machine learning. We incorporate design of experiments, lots of simulations. In this case, I'm showing some CFD simulations. There's a curation of the data, and then we provide it, use this data to train a neural network. And a typical approach that I like to use is to use the autoencoder. So the autoencoder, you can see, will take the phase space, the state space of the data. This is the temperature distribution over all the space, the velocities, the components of the velocities, the molar fractions of materials, whatever is used to represent the state of the system, and it learns how to replicate itself. But the information has to go through a bottleneck, and that's this Z layer right here. This is actually a way of reducing into a lower dimensional space. This is akin to like a principal component analysis where you have these principal components. But with this autoencoder, it's like a nonlinear PCA. So once we have this well trained, we can it projects out and replicates the state space accurately within a certain tolerance. We can train a new data set, and this new data set can be the control parameters and maybe some design parameters, and we can train that to correlate with a point in the latent space in this reduced dimensional space. And this can be done with far fewer data points at this point. The advantage here is that we get the projection out to the state space from over here for free. So we bring this over, and now we can correlate the design space and the control space to the state space of the simulation. And so the main points that we're capturing here is that these neural nets can learn to predict these very complex processes. Simulations can provide the training data. That's a key point here. And then we can take these physical experiments or this production data and integrate it into a better predictor model. And so we have these tools and resources like the Merlin system, and that's actually open source. We've used that for our at the National Lab for our National Ignition Facility. So we have simulations of this inertial confinement fusion, and we've used that to elevate to train this data and these deep neural nets, and used our data from our National Ignition Facility. We're doing target fusion physics, and that's where the Merlin system has been developed, and now it's open source for other folks to use on their high performance computing systems. So the impact of this these programs is that these reduced order models actually can run much faster. I didn't mention that in the glass simulation, those simulations are very complex. They're multi-species, multi-phase. There's issues that the energy transfer is speed of light because the glass is transparent to the material. But then there's the molten flow, which is very slow. So you have speed of sound issues, a very stiff problem. It can take several days to actually run those to completion. When the production was having problems, they would have to launch 4 simulations on their local cluster. They would get the data back in 4 or 5 days, and then they would have to reset the production from their best guess of those four simulations, run it for a few days. Meanwhile, all this molten glass was actually had a lot with lots of flaws, would have to be taken out of the end of the system and recycled. So this was a big waste of production. The data integration can actually make the most out of the sensor data that is used in these production facilities, and we use uncertainty quantification to help figure out where the best bang for the buck is. How can you get the information that is the most useful? Is it more simulations? Is it better instrumentation? Is it more physical runs? So we can help with all this with this program. So these project impacts that we've helped on these different projects. For the glass companies, we've saved about 2 weeks of production per furnace, and if we extrapolate that to the U.S. glass industry, that saves about 2.5 tera-BTUs of energy, and avoids about 130,000 metric tons of CO2 emissions. For the aluminum companies, by their estimation of how much they're saving is about $60 million a year if they can reduce half the scraps from their casting facility. And they estimate that the U.S. primary casting could save about $365 million a year if by reducing 50% of their scrap waste. We're also helping companies like Vast Power Systems They are actually generating power using these gas turbines that are on the ground and using water to cool them, but they're figuring out how to put the water, inject the water in order to reduce the nitrate emissions. We're also working with the steel industry, AK Steel, ArcelorMittal, and their estimate is that they could save around 3 petajoules of energy, or about $30 million a year, by reducing some of their issues with bad casting formations. And so I think I've ended a little early, but I guess we could start the Q&A session at some point. And I'd like to actually do a little advertisement for our manufacturing day, actually, before we get to there. So in the United States, we have this long time-honored tradition ever since 2019. We celebrate Manufacturing Day on the first Friday of October. And so we are doing a lot of talks, and I will actually be presenting some of my work there. And you can also sign up and have one-on-one conversations with the speakers. And to register, you go to hpcformanufacturing.llnl.gov. And I would also welcome you to link in with me on LinkedIn. And at that point, I will end my talk.
Thank you very much. Thank you. I think yes, now we are enter to the Q&A session, and I think I will facilitate this session. So if anyone has any questions, please leave your question in the chat box or Q&A box, and then we will pick up your question for the panel to answer. And let me look at so are there any questions from the panelists that we will want to start asking the speaker here?
So I have a question for Professor Shua.
Sure.
About the active learning algorithm. So you do an explore versus exploit, and that's very interesting. And you say that you do a trade-off, and I'm wondering what is that? How is that trade-off determined, and how is that different from just saying, I'm going to go find the areas that have the greatest uncertainty, or I'm going to go search the areas that have the greatest optimal value. It looks like it sounds like you do a trade-off to mitigate the uncertainty and search for optimal at the same time.
Oh, right. Okay, so let me share my screen.
Yes, please. Yeah.
Okay, so what we did is we know that exploration, we want to find the data points or the experiment with the largest uncertainty. And for exploitation, we just believe in the predictions. We just choose the best predicted value. So, but in reality, we don't know whether the model is good or not. So we can do like several explorations and then do some exploitation. But we won't do it at the same time. We do the balance trade-off. So we would like to define a utility function, so which both related to the uncertainty and related to the predicted value. So we use such kind of a utility function to rank all the possibilities, and we select the one with the highest score with respect to the utility function. So how this slide shows one way to define the utility function. So we actually calculate the shaded area. That is the possibility to improve, to have the better value if we do the experiment, the probability. Then we times the probability with respect to the improvement I. The I we define here is the maximum value between the y minus best so far and the 0. If the predicted value is below the best so far, we consider it is 0. If it is higher, then it's y minus f max. So that is the improvement. We times the probability with the improvement and do the integration, then we get the expected improvement of the property. So this is the utility function we used. This utility function is both related with the predicted value. If the predicted value is high, we have higher EI, expected improvement. And it's also related with the uncertainty. If the sigma here, the standard deviation is high, is large, then the expected improvement is also large. So by defining such kind of a utility function, we can do some balance trade-off between the exploitation and exploration. This is what we did.
Yeah. Yes, it's actually this is the same question as Professor Tong here to ask you. Would you like to comment on how to balance the exploitation and exploration?
Okay. Yeah, this is just one way to do, and the simplest way is just to add the predicted value with the standard deviation. So put the two values together, then so this utility function, we call it UCB,
Sure.
which is balance, which will balance the exploitation and exploration. I don't know whether this is okay for you.
Yes.
Great, thank you.
Yes, great. Thanks, Vic, as well. In the chat box here, we have another question, probably to Enzo. Compare with the casting process for the welding application. Is that possible to predict the microstructure evolution and predict the weld defect using the machine learning? I'll probably open to all panelists here. He's not indicate who's going to ask.
So, which question is that? Where is it?
Yes, for welding application, is that possible to predict the microstructure evolution and predict the weld defect using machine learning? I mean, compare with casting process.
Well, I guess it's possible. How accurate it is, I'm not sure. Yeah, welding is a kind of like I'm sure. Yes, I think probably I'm not the best person to answer this question. Probably.
Yes. Are there anyone in the panelists has anything to add? Please do so. Otherwise, I will go to specific question to you. And so there's someone asking, could you please elaborate a bit more on the combined effect of cooling rate and the cooling on nucleation?
Yeah.
You can show your slide if you want.
Yeah. So a second. So I think latent effect of cooling rate is interesting because what is known and is actually effectively known by theory and by experiment is that in any casting, if you increase the cooling rate, you ended up with a grain size that is smaller. That means that you got more nucleation. That's what is actually what we observe in our data as well, and that would be concerning if it wasn't. So sorry. So like these data show, like when you increase the cooling rate, the crystal
Yes.
formation rate increase, right? So that's actually
Yes.
expected. The correlation is that we saw that when you start to vary the solute content as well, the effect of cooling rate, sorry, the effect of solute content is correlated to which cooling rate you're using. In other words, when you don't have, when you are cooling very slow, essentially increasing your solute content doesn't really affect the crystal formation rate. While when you start to increase the cooling rate, the effect of solute is more evident, right? And we believe that essentially all of this is related to essentially this little explanation here, and is actually related to the fact of how the undercooled zone is developing. So the undercooled zone is essentially how much driving force there is in the liquid that is not yet solid, right? So the undercooling drive both the growth of the grain and the nucleation of the grains, right? So there is a balance between them, like, and depend of how much, we call it solute suppression. So while when you got a mixture of solid and liquid, right? So some of the solid, when is forming, is essentially growing, but in growing is actually ejecting solute. In this case, is the blue, right? In an alloy that is more richer in solute, essentially this blue area is for the same solid fraction is higher than in when you got less solute. And the effect of it is essentially that you suppress more of the easy nucleation to actually achieve essentially nucleation or higher undercooling. But the size distribution of the nuclei in the liquid is log normal, right? And because of this reason, essentially, if you kill the potent nucleant, which are not very diffuse, you basically are able to activate more nuclei, right here. That's the effect of solute. The cooling rate instead is not shown in this data, but essentially it has an effect on the shape of the diffusion zone, right? And it basically can be explained with a similar argument. When you increase the cooling rate, you essentially narrow the diffusion length and you increase this effect.
Yes. Thank you very much for your clear answer on this. I think there's some, I think we have today, Professor.
We'll have more questions in the chat.
Yeah, we have more questions. Yes. Just to answer to the previous question on welding application, Professor, I think we have Professor Harry Badeshia here. He said, yes, the microstructure and property of the weld has been extensively treated using machine learning, a lot of literature. I think answer to someone question, I think, yes. Sure, there's another question to Victor, on, I think from Professor Tong, he asked you, do you mention using the auto encoder to learn efficient data coding? Will this have any effect on accuracy?
So it does to some degree, but we're able to get a pretty good representation of the state space on both sides through the autoencoder. And one of the neat examples, so first of all, we use lots of simulation, so we have lots of data from here. In addition, we find we have some ways to use data augmentation, and this is actually the key thing. With data augmentation, with images, they would take the image and they would skew them, or they would rescale them, or translate them. With simulation, we have a way of doing an analogous method to augment the data. So we have lots of data to train these this autoencoder that has lots of weights. But another advantage is with this latent space, we can actually map out. We can reduce it in a way that we can map out easier where the better locations in this latent space are for production. We can actually map scalars such as production flaws into this latent space pretty well. And then that is a background or a start for a control algorithm. So we can actually consider where you are in this latent space and what is the better direction in this latent space to get to a region that has fewer flaws based on the simulations or based on the production data.
Cool.
And so this is we're actually starting to explore a new control algorithm on this.
Victor, just following on what you have said earlier, you said you have two set of dates, experimental and simulation dates.
Right.
Use this to training and validation your models. If you have different combination of experimental data with simulation data, will this affect this training efficiency or accuracy?
Yeah. So the transfer learning is actually done on a second stage. It's not actually done on the autoencoder itself. We're able to one of the main things that we're doing is mapping the production data into this latent space, and that turns out to be very useful in itself. The transfer learning itself, we can actually get pretty good replication, somewhere on the order of in the high 90 R squareds. So it's good enough for these production simulations or these production situations.
Thank you. Yeah.
Yes, thank you. Actually, I have a question probably to everyone, to the panelists here. So do you present me, for example, we present the CFD simulation for, I think, fusion, nuclear fusion application, right? Are there any other materials or manufacturing case study that we apply AI and successfully implemented in the real application? Do you have any comment? I mean, probably apply to new material discovery as well from Professor Xue, and then Enzo for new certification and you have any other case study that successfully implement this type of AI, application of AI in the real application?
So let me, I'm actually using this on some COVID-19 antibody studies.
Sure.
And so
antibody, okay.
Yeah.
Okay.
So the antibody, what we're studying is perturbations, mutations on an antibody. That this antibody was effective for SARS-1, and we're doing mutations for this SARS-2 COVID. And we are, if you look at all the possible mutations within that we're interested in, the number of perturbations, combinations that we can study is about Avogadro's number. So it's a very large exploration space. What we've done is we've reduced this to represent to these representative features of the antibodies, which is more of a 58-dimensional, well, actually it's more like an 86-dimensional space, but some of the studies we do are a little bit lower. And we're able to reduce this into a latent space and actually look for regions that have high change in energy, change in free energy. So you want to minimize the change in free energy between the antibodies and the antigens. And so we're actually using the same method for that, which is very different because it's a discrete space as opposed to these continuous spaces from these CFDs studies. So it this method is starting to show pretty good generalization.
Sure. Are there any application closer to the metal or metallurgy application? For example, additive manufacturing. Is that I'm sure that there's a program in Lawrence Livermore working on that. Is that applied?
We are studying metal additive manufacturing quite a bit. We published, we did some work, and we actually published a seminal paper on this keyhole effect from actually, we did the design of experiments and found regions where you can actually get this keyholing. We have not applied the AI methods to that yet, although there's another researcher doing really good AI machine learning prediction of these additive manufacturing of polymers. So
A polymer, okay.
yeah. So we'll probably be doing looking into the metal additive manufacturing pretty soon. We have a really nice lab now for doing that and doing additive manufacturing of reactive materials like titanium and aluminum and other materials like that.
Yes.
I'm also working with steel industry on the cold rolling process.
Cold rolling process, yes.
Yeah, I don't have that yet. And then we have another steel industry partner looking at casting defects. So those are still, we're still in the simulation process of those. And then we'll do the machine learning and probably have something to report in about 6 months.
Of course, probably next time.
We are doing something similar in predicting casting defects and also predicting mechanical properties of steels. And then, for example, look at property prediction, and then if you look into strength and look at ductility, and then probably our value can get to higher 90, 97, 98, or even 99. And then if you look at this fracture toughness data, and they are quite low, looking to probably 80-ish or 90, very low 90s. Yeah, we are not very sure, but we probably suspect a couple of reasons. I'm not sure how I want to discuss. You know, probably this is we said this is kind of a stochastic effect because fracture toughness depends probably on the largest defects in the materials, and then you this kind of small possibility to occur, and then you either need large data or we have not found something which is a key data in the input yet. Yeah, in the input mainly we essentially use chemistry and processing, and we ignored this the essential part with microstructure defects. You have chemistry, you have processing, and then you predict the properties. Yeah, we may have something which is missing in our try very hard. We have large set of data. We're working with the industry. We look into because that has been recorded for a long time. So for the mechanical prediction, some of them we said, well, we're quite confident we can do it, but for fracture toughness, we can find we have less confidence in comparing with other property prediction.
Yes.
We're using the software. There's a public domain software called Hot Strip Mill Model, HSMM, and so we're actually using that to generate, tens of thousands of simulation points on our machine. It is designed to run on a PC in the plant, and it's very good at predicting the microstructure at the head, tail, and midsection of a roll. We're looking to expand the prediction to do in real time hundreds of points along the strip, and so again, and even through the depth, trying to figure out what the microstructure should be within that rolled steel.
Yeah. Okay, you got microstructure into play, and before, okay, this is something we have not tried yet. We use input mainly chemistry and processing variables, and this is what happens in the industry. Look in the steel making industry, they know this, they do not know microstructure, anything like that. Yeah.
I think probably one of the last question to Professor Xue. You mentioned that you have a case study in shape memory alloy, nickel titanium 90. Yes. Are there any more complicated system that tertiary or quarterly or high entropy alloy that you apply your method to look into the new material discovery or not? You have any example?
Yeah, we have applied these similar methods, approaches, the balance trade-off to explore, to try to find the high entropy alloys with higher hardness. So, and we also do some active learning method to do the classification of the high entropy alloys to classify the BCC, FCC, and the dual phase high entropy alloys.
Okay.
And we also do some optimization of the processing conditions to the magnesium alloys. We do some multi-objective optimization. We have two goals to achieve higher strength and higher ductility. You know, they're exclusive, but we want to use the multi-objective optimizations combined with these optimization algorithms, the trade-off algorithms to quickly find the better balance trade-off between them, and using the two-step aging process in the magnesium alloys. Yeah, that's what we.
Very interesting. So this is work in progress at the moment. It's not published yet, or you're working on this now.
Now we have published it. We already published them, and now we are working on, you know, just now the processing is just in one stage, in the heat treatment stage. Now we want to expand it to the whole process and see whether this method can help. Yeah.
Yes, thank you very much. So I think I will hand over back to Jenny now to probably wrap up the session for today. Yes, thank you.
Yeah, so I'd just like to thank all our speakers again, and our virtual audience for your attention and contributions of those questions. So next week we have the fourth in this series of webinars. So it's next Wednesday, the 30th, I believe, at 12:30 UK time. Are we back to the same time?
Seminar start at 1 p.m.
1, sorry, yes. 1 o'clock, sorry. Next Wednesday, the 30th. Yeah, so the focus will be on the industry response to the digitization and AI initiative, and it will include some real project examples, so a more sort of applied seminar session next week. So with that, I hope to see lots of you next week, and thank you very much for attending this week.